Welcome to video 16.2. Our focus will be on activation energy. I really couldn't find any chemistry humor related to activation energy, so we're going expensive. For accessing your prior knowledge, Maxwell-Boltzmann distribution curves will be helpful. Remember, this is energy or velocity on the x-axis and probability or number of particles on the y-axis, and we get some sort of distribution approximately like that. If I raise the temperature, it broadens the shoulder a little bit. Also, just sort of remembering rate of reaction calculations is going to be helpful as well. So let's look at some syllabus statements. There's a whole lot of statements on here that we'll cover, including something called the Arrhenius equation. We'll see that these equations are given in the data booklet, which is helpful. So let's do a little bit of a thought experiment. Let's say that this reaction between hydrogen and iodine is first order for hydrogen and first order for iodine. And rate is therefore equal to K, some constant K, times the concentration of hydrogen times the concentration of iodine. So what happens to the rate when the temperature increases, but the initial concentrations of hydrogen and iodine are kept the same? Thought experiment. What happens to the rate? Well, we should know that if I increase the temperature, I increase the rate. Partially because of that Maxwell-Boltzmann distribution curve. So if I look at the Maxwell-Boltzmann distribution curve at two different temperatures, at a higher temperature, more of the particles as a percentage, a greater percentage of the particles have enough kinetic energy to overcome the activation energy barrier, and it increases the frequency of collisions because the particles are generally moving faster. So what is the significance of this? If I increase the temperature, I increase the rate. How does that relate to this equation? What is the significance? That means that the rate constant K is temperature dependent. So K is unique to a reaction and a temperature. And that is significant. So if I calculate the rate constant K, I am calculating it for a specific temperature. So if I look at Maxwell-Boltzmann distribution curves at different temperatures, if the activation energy is large, so let's say the activation energy, the velocity required to meet the activation energy is here. This is a high activation energy. Then heating the particles causes a significant change in the number of particles that have the required activation energy. But if I have a low activation energy barrier, change in the temperature doesn't change it very much. That means the temperature dependence of K depends on the value of the activation energy. If I have a high activation energy, there is a large variation in K with temperature. If I have a low activation energy, then it will be a small variation in K with temperature. And that's helpful information in terms of processing these ideas. This gives us the Arrhenius equation given here. I'm not going to derive the equation for you. I'm just going to accept it as an equation and move on. I'm sure we can find a derivation somewhere if you really are curious. Lowercase k is the rate constant. A is the Arrhenius constant, which we'll talk about. E is the natural log form of E raised to the power of negative activation energy over RT. So let's talk about these. We know the rate constant. We know R, the ideal gas constant. We know temperature is in Kelvin. Got to have Kelvin. But let's talk about A. It is sometimes called the pre-exponential factor because E is exponential. Sometimes called the frequency factor. I have even heard it called the collision factor. Although it also is related to the energy required for a collision to be successful. Essentially, the larger the A, the more likely a collision will be successful. So it measures on some level the percentage of successful collisions for a given reaction, and it's related to the geometry of the collisions that are required and the energy that's required for that collision. Kind of related to the activation energy, but it's a separate factor. And so A is specific to a given reaction. Every reaction has a specific value for A. It's related to collisions, related to energy. And as I mentioned earlier, this equation is in the data booklet, and it even tells us 16.2. Very nice of the IB to do that for us. Now, what if I take the natural log of both sides of this equation? And there's some algebra and stuff going on here that I'm not going to worry about. I'm going to trust it. If you understand the algebra, good for you. If I take the natural log of both sides, I have the natural log of K equals negative activation energy over RT plus natural log of A. A is a constant. So I have essentially y equals mx plus b, where y is the natural log of K, the slope is the negative activation energy divided by R, and x is 1 over temperature, and the y-intercept is the natural log of A. So that means if I'm going to draw a graph, natural log of K is the y-axis, and 1 over temperature is the x-axis. And if I know the slope is negative activation energy over R. R is a constant. So I have a way of finding the activation energy for a reaction. If I conduct a reaction at multiple temperatures, I can make this graph and I can find the slope and I can calculate the activation energy. And that's kind of where this is headed. That's the direction we're going. So here we have a plot of 1 over T and natural log of K as the y-axis. And the y-intercept is the natural log of A from this form. And the slope, the gradient, or slope, from where I come from, is negative activation energy over R. So if I can calculate the slope, I can calculate the activation energy. Lucky for us, this equation is in the data booklet. You have to remember that y equals mx plus b is the form for that equation, and the slope is negative activation energy over R. So let's look at a sample problem. 5 different temperatures. I have a constant K, the rate constant, calculated at 5 different temperatures. Determine the activation energy for the reaction in kilojoules per mole by a graphical method. Graphical method means we're going to plot 1 over T, and we're going versus natural log of K, or natural log of K versus 1 over T, depending on your vocabulary. So I need to calculate 1 over temperature for each of the temperatures, and I need to take the natural log of each of the values for K, and I need to plot them. And then I will determine the slope, and the slope is negative activation energy over R. So this is just what I basically just said, except written in nicer words and more readable format without my horrible handwriting. Convert the values of K to natural log of K, and the values for temperature to 1 over T. But remember, this is Celsius, so I need to convert to Kelvin. I forgot that step in my previous slide. I apologize. So plus 273, and then 1 divided by that. 1 over whatever the value is in Kelvin. So here's our graph. Natural log of K is the y-axis. 1 over temperature is the x-axis. The units are 1 divided by Kelvin, or Kelvin to the -1, and that's a capital K. I know this is a bit confusing. This is lowercase k for natural log of K. Keep those straight. So the measured gradient is negative 9518.65 Kelvin. Now, where did this value come from? There are a couple ways to do that. Recall that slope is rise over run, so it's y2 minus y1 over x2 minus x1. Pick 2 points, calculate the change in y, calculate the change in x, calculate the slope. I know that the slope is negative activation energy over R, so that means activation energy is slope times R. So if I redo this, activation energy is negative slope times R. The slope was negative, so if I take the negative slope, it becomes a positive times R. Therefore, the activation energy is 79.1 kilojoules per mole. So I'm just kind of asking you to follow along here and sort of develop an algorithm for using K values, rate constant values, and temperature values to solve for the activation energy. If I know the slope, I can calculate the activation energy. Now, there is a way to solve for K just using 2 temperatures. It involves a little bit of algebra. It's kind of like a system of equations, if you will. And if you don't want to follow along on that algebra, well, here you go. Natural log of K1 over K2 equals the activation energy divided by R, in parentheses 1 over T2 minus 1 over T1. Do you have to memorize this equation? Nah, it's in the data booklet. So on our previous slide, this was called the graphical method. Geez, I'm not, sorry, my handwriting is just not very good today. I know, it's never good. This was called the graphical method. This is using 2 temperature values to find the activation energy. There it is in your data booklet. We have 3 equations for 16.2. So if I know the temperature, this is Celsius, so add Kelvin, add 273 to get to Kelvin, and I know the rate constant, I can calculate the activation energy for the reaction without making a graph. So I'm going to convert Celsius to Kelvin, and then I'm going to substitute into this equation. Now, does it matter which one is K2 and which one is K1? Well, this is T1 and this is K1, T2, K2. As long as I keep these consistent, it doesn't matter whether this is T2 and K2 and T1 and K1. As long as I keep them consistent, I will get the same answer. So the natural log of 3.52 times 10 to the negative 7th divided by 3.95 times 10 to the negative 2nd equals EA over R times 1 over T2 minus 1 over T1. This involves doing a bit of algebra on your calculator. Maybe order of operations is going to be quite important when you do this. And we're going to solve for activation energy. Activation energy is 1.87 times 10 to the 5th joules per mole. I am doing a bit of assuming here that you can handle the algebra. If you need some help with it, ask me in the Google form, ask me during class, ask me through an email. I'm happy to take you through the algebra a bit there. Checkpoint question. Consider the following statements. The rate constant of a reaction increases with increase in temperature. Increase in temperature decreases the activation energy of a reaction. The term A in the Arrhenius equation relates to the energy requirements of the collisions. Which statements is or are correct? Do some thinking. Come back for the answer. The answer is C. An increase in temperature does not decrease the activation energy. That's false. The rate constant does increase with an increase in temperature. That is true. The term A in the Arrhenius equation relates to the energy requirements of the collisions. The key here is it's related to the collisions. I'm a little bothered by the fact that it's called energy requirements here because it's more about the collision orientation, but it does relate to the energy. And it's just kind of something we need to know about A. And so the correct answer here is C. So as a summary, the rate constant K is temperature dependent and increases with increasing temperature. And the Arrhenius equation can be used to graphically determine the value for the activation energy, EA. Maybe there's some other summary points you want to add as well. Now I've got another practice problem for you. There is some data for you to analyze. Take the data, analyze it, and we'll talk about it in class. Thank you for listening. I've got a Google form where you can put your answer to the checkpoint question, where you can put questions, and where you can put feedback. Thanks again for listening. Have a great day. I'll see you in class.